In this videotape, we will practice evaluating limits of various algebraic functions. Trigonometric functions will be handled in another tape. Since this is a review, we will assume that you have already seen the various limit theorems and you're familiar with the idea of continuity. For example, you are aware of the fact that limits of continuous functions can be evaluated by substitution. Okay? We'll call on any of these ideas that we need as we go through the problems. For our first example, let's evaluate the limit as x approaches 4 of x squared plus 8 over x plus 4. Here we can say that the limit of a quotient is the quotient of the limits. It's the limit of the numerator divided by the limit of the denominator, because the limit of the denominator is not 0. Okay, so it's going to be the limit of the numerator divided by the limit of the denominator. The denominator is not going to 0. And since these are both polynomials, and we know polynomials are continuous at all real numbers, we may evaluate these limits by substitution. So the limit of x squared plus 8 as x approaches 4 is 4 squared plus 8. The limit of x plus 4 as x approaches 4 is 4 plus 4. And we have 16 plus 8, 24, divided by 8 for an answer of 3. For our second example, let's look at the limit as x approaches 4 of x squared minus 5x plus 4 divided by x minus 4. Now this problem is going to be a little bit more difficult because we can't simply say the limit of a quotient is the quotient of the limits, because in this problem the denominator is going to 0. As x approaches 4, the limit here is 4 minus 4 or 0. The first thing we should do is look upstairs and see what the limit of the numerator is. The limit of the numerator, this is also a polynomial, we can evaluate its limit by substitution, would be 4 squared, 16, plus 4, 20, minus 5 times 4, minus 20. 20 minus 20 is 0. So we have a situation where the bottom is going to 0 and the top is also going to 0. This kind of problem, okay, usually we can do something else with this problem. We cannot make a decision at this stage. Okay, if the bottom was going to 0 and the top is not going to 0, that limit does not exist. Then we can be definite. Okay, if the bottom went to 0 but the top did not go to 0, that limit would not exist. However, when the bottom goes to 0 and the top also goes to 0, we cannot make a decision at this stage. We want to see if we can do something with this problem so that we will be able to figure out its limit. One thing we can do is, let's go over here and look at this function that's under consideration. We are examining the function x squared minus 5x plus 4 divided by x minus 4. Okay, we have sketched problems like this in class. If you factor the numerator here, this is x minus 4 times x minus 1 divided by x minus 4. The domain of this function f is the set of all x values such that x is not equal to 4. Now, there is a strong temptation to cancel the x minus 4's here and to just be left with x minus 1. When you do that, you have to remember that when you're canceling x minus 4, you're really dividing numerator and denominator by x minus 4. And we have to make sure we're not dividing by 0. So if we say x is not equal to 4, then we would be permitted to cancel the x minus 4's. We could get x minus 1 as this function being equivalent to x minus 1, so long as we say if x is not equal to 4. Now, the graph of this function, y equals x minus 1. Okay, its graph would be a straight line. if we had y equals x minus 1. If x is 0, y would be minus 1. if y is 0, x would be equal to 1, and it would look something like this. It would go through 0, minus 1, and 1, 0. Okay, now that's the graph of y equals x minus 1. But the domain of this function f is all x but not equal to 4. So we have, basically what we're going to get is a line with a hole in it. Okay, if x had been equal to 4, y would be equal to 3. 1, 2, 3, 4. This is the point 4, 3. Okay, the graph of y equals f of x looks like this. It's a line with a hole in it. The graph of y equals x minus 1 is just the entire line. Now, let's go back over here and look at this problem. We want to find the limit of this function as x approaches 4. As x approaches 4, it's assumed here that x is not equal to 4. It's merely getting close to 4. Well, if x is not equal to 4, it would be simpler to find the limit of the function x minus 1. Remember, we said that as long as x is not equal to 4, this function and x minus 1 were the same. Let's go back and look at the picture again. X squared minus 5x plus 4 over x minus 4 is the same as x minus 1 so long as x is not equal to 4. Okay, y equals x minus 1 is the entire line. The original function that we had, x squared minus 5x plus 4 over x minus 4, is a line with a hole in it. As x gets close to 4 but is not equal to 4, these two functions are really the same. Therefore, we can use a simpler function to evaluate the limit. So going over here, we have now a much simpler problem. We want to find the limit of x minus 1 as x approaches 4. This is a polynomial. We can find its limit by substitution, and we get 4 minus 1, or 3, as an answer. Now, we don't always have to go and sketch the graph of the function. We can simply put in an extra step over here without sketching to say that this is really x minus 4 times x minus 1 divided by x minus 4. And as x gets close to 4, x is not equal to 4, just getting close. So x minus 4 is not 0. And we can divide numerator and denominator by x minus 4 and then go back into this step. So we can go this way, and we can eliminate the sketching the graph. We're just going to do it algebraically here. But we understand that basically what we're trying to do is to find a simpler function that looked just like this function so long as, as long as x was not equal to 4. For our next example, let's try this. The limit as x approaches 4 of x squared plus 8 over x minus 4. Once again, we cannot say simply it's going to be the limit of the numerator over the limit of the denominator because the denominator is going to 0. So we immediately look upstairs and we see what's happening here. X squared plus 8, as x approaches 4, this is going to 4 squared, 16 plus 8. The top is approaching 24. In that case, if the bottom goes to 0 and the top does not go to 0, this limit does not exist. Okay, let's try our next example. The limit as x approaches 4, the square root of x minus 2 over x minus 4. Here, as x approaches 4, the bottom is going to 0, and the top, the square root of 4 minus 2, is also going to 0. This is our tip-off that we might be able to do something with this problem. Okay, what we're going to do here is to try to modify the form of this function. If you remember, before we had a polynomial over a polynomial, we tried factoring and canceling. When we're involving a square root here, what very often works is to multiply by 1 in the following form. You see where it says the square root of x minus 2? Multiply top and bottom by the square root of x plus 2, the conjugate of the numerator. Now, first of all, we're multiplying by 1. That's always a legitimate thing to do. Okay, we're multiplying by 1. That's okay. What we're doing is, in a sense, is rationalizing the numerator. Now, I know that you've always been brought up to rationalize denominators, but when we're working out these limit problems, sometimes we rationalize the numerator. We do whatever works for us. The idea is to try to rewrite this into another form whose limit will be easier to evaluate. Okay, let's see what we have here. This is the limit as x approaches 4. Now, the denominator is somewhat messy. It's x minus 4 times the square root of x plus 2. But the numerator has simplified. Here we have, say, a minus b times a plus b. If we multiply these two together, we'll get a squared minus b squared. Or if you use the FOIL method for multiplying binomials, we have first square root of x times square root of x, that's x. The outer is 2 times the square root of x. The inner is minus 2 times the square root of x. They drop out. And for last, we have minus 2 times 2, or minus 4. Okay, so we have x minus 4 divided by x minus 4 times the square root of x plus 2. Now, as x approaches 4, remember, x is not equal to 4. It's just getting close to it. Well, if x is not equal to 4, x minus 4 is not equal to 0. And we can divide numerator and denominator by x minus 4. If you divide x minus 4 by x minus 4, you're left with a 1, not a 0. When you cancel out everything in the numerator, a 1 remains. So we have here the limit as x approaches 4 of 1 over the square root of x plus 2. This function, okay, when x is not equal to 4, is equivalent to the original problem that we were given. Let's look back over here. This was the original problem, which was in the 0 over 0 form. Okay? We multiplied by 1, and then we canceled the x minus 4, which was legitimate so long as x was not equal to 4. If x is not equal to 4, this is equivalent to the original problem. Well, this is a much easier limit to evaluate. Here we can say it's the limit of the numerator divided by the limit of the denominator. The limit of the numerator, the limit of a constant, is just that constant. The limit of 1 is 1. The limit of the denominator, it's the limit of this plus the limit of that. The limit of the square root of x is the square root of the limit of x, or the square root of 4, as x approaches 4. The limit of 2 is 2. This time we can just evaluate the limit by substitution, and we get 1 over 2 plus 2, or 1/4, for an answer. For our next example, let's try the following. The limit as x approaches 4 of 1 over x minus 1 over 4 divided by x plus 4. Here we would like to say the limit of a quotient is the limit of the numerator divided by the limit of the denominator. So the limit of the numerator, the limit of 1 over x as x approaches 4, that's 1 over 4 minus the limit of 1/4, which is 1/4, over the limit of this polynomial, which is simply 4 plus 4 as x approaches 4, and we get 0 divided by 8 for a final answer of 0. Remember, there is a problem if the bottom goes to 0 and the top doesn't. That limit would not exist. If they both go to 0, then we try to see if we can somehow modify the form of the function so that we can evaluate its limit. But if the top goes to 0 and the bottom does not go to 0, there's no problem. 0 divided by 8 is 0. For our next example, let's evaluate the limit as x approaches 4 of 1 over x minus 1 over 4 divided by x minus 4. Okay, this is similar to the preceding problem, except we have here now x minus 4 instead of x plus 4 in the denominator. And now, of course, as x approaches 4, the bottom is going to 0, and the top, 1/4 minus 1/4, is also going to 0. So we're going to try to do something with this. Okay, once again, we're going to fall back on our idea of multiplying by 1 to modify the form of the function. And when we multiply by 1, this time we're going to multiply by 1 in the form 4x over 4x, the product of the denominators we're using here, 4 times x. This is a very common technique in simplifying complex fractions. Perhaps when you studied complex fractions, you had a problem like this, 1/3 minus 1/4 divided by 5. There are two ways that we can approach this problem. One way is to say that 1/3 is really 4/12, and 1/4 is really 3/12. Combining, in order to subtract fractions, they have to have the same denominator, divided by 5. This gives us 4/12 minus 3/12, 1/12 divided by 5, which is 1/12 divided by 5 over 1. And then we invert and multiply by 1/5, giving us an answer of 1/60. That's one way you're taught to handle complex fractions. Another approach, and I think preferable in this kind of problem, is the following. We take our problem, 1/3 minus 1/4 over 5, and we multiply by 1 in the form the product of the denominators over the product of the denominators. So 3 times 4, or 12 over 12. Now let's see what happens. We have 1/3 times 12. We have to distribute the 12 through the parentheses. So it's 1/3 times 12, which is 4, minus 1/4 times 12, which is 3, over 5 times 12, which is 60, giving us, of course, the same answer of 1/60th. And what we're doing in our problem with the limits is basically handling something like this, where we have a complex fraction. I think this is the easiest way to go, to multiply by 1 in the form the product of the denominators over the product of the denominators. So now we've done it with numbers. Let's try it over here with the algebra. This is the same thing that we had before, like 1/3 minus 1/4 over 5, the same idea. Okay? The limit as x approaches 4. Now, the denominator is simply going to be x minus 4 times 4x. In the numerator, we're going to have this 4x has to be distributed through the parentheses. It's going to be 1 over x times the 4x minus 1 over 4 times the 4x, which gives us the limit as x approaches 4 1 over x times 4x. This is really 4x over 1. The x's cancel. We have 4 minus 1 over 4 times 4x over 1. The 4's cancel. We have just the x over x minus 4 times 4x. Now, we're not quite at the stage that we can cancel things out, but if you factor the numerator, and it's not something that you ordinarily think of doing, okay, but if you were to rewrite the numerator, 4 minus x, as minus 1 times x minus 4, let's see if that's right. Minus 1 times x, that's minus x. Minus 1 times minus 4 is plus 4. So we have minus x and plus 4. Then things would look a lot better. Okay, if this were true, and it looks to be true, minus 1 times x plus minus 1 times minus 4 is minus x plus 4. Okay, so that's equivalent to that. then as x approaches 4, it's not equal to 4, right? So we can divide numerator and denominator by x minus 4. That's not equal to 0. And we have now the equivalent problem of finding the limit as x approaches 4 of minus 1 over 4x. Once again, we have gotten this down to a form whose limit is of a function whose limit is much easier to evaluate. Here, we can say it's the limit of the numerator divided by the limit of the denominator. As x approaches 4, that's going to be 16. And the answer to this problem is minus 1/16. Now, just a word about this factoring that I did over here. I said that 4 minus x was minus 1 times x minus 4. Okay, now that's a little non-traditional factoring. If I had said 2x minus 8, I wanted you to factor that, I think most of you would be able to do this. You would say it's 2 times x minus 4, 2x minus 8. If we're dealing with 4 minus x, think of it as minus x plus 4. And just the same way we factor the 2 out in this part, we could factor out a minus 1. We just don't usually think in terms of it, but minus x is really minus 1 times x. And I can factor out the minus 1 the same way I factored out the 2. And I'd be left with x minus 4. And just like you can check this and say, well, this is 2x minus 8 using the distributive law, this works. This is minus x plus 4, this works. So remember that 4 minus x can be rewritten as minus 1 times x minus 4. And that's really the hardest part of this problem. Let's go back and look at the problem from the beginning. Just review it one more time. We were given a limit problem. The bottom went to 0, the top went to 0. It involved fractions. It was a complex fraction. The trick was to multiply by 1 in the form the product of the denominators over the product of the denominators. The denominator was x minus 4 times 4x, no problem. The numerator, the 4x, had to be distributed through the parentheses. So we had the 1 over x times the 4x minus the 1/4 times the 4x. Here, the x's canceled. We were left with a 4. Minus here, the 4's canceled. We were left with an x. And then we used our factoring. A little tricky here, but we were able to factor 4 minus x into minus 1 times x minus 4. The x minus 4's were then canceled. And then we had an equivalent limit problem that was much easier to solve. And the limit was minus 1/16. For our last example, let's look at a split function. F of x is equal to minus x if x is less than 0, the square root of 9 minus x squared if x is between 0 and 3, including the endpoints, and x minus 3 if x is strictly greater than 3. Okay, so it's a split function. There are 3 parts to it. Something to do when x is less than 0, something to do between 0 and 3, including the endpoints, and something else to do when x is greater than 3. I'm interested in this particular problem. I want to sketch the graph of this function f and evaluate the limit, okay, and find the limit of f of x as x approaches 0 and the limit of f of x as x approaches 3. Now, to sketch the graph of this function, the best thing to do would be to graph individually each of the parts. Let's look and see what y equals minus x looks like, what y equals the square root of 9 minus x squared looks like, and y equals x minus 3. Let's sketch each part separately, and then we're going to cut and paste pieces from all of these functions together to form this function f of x. Well, I'm not going to worry about the restrictions in each case. I'm just going to try to graph the function in its entirety, and then we'll cut and paste in a few moments. Okay. Right here we have equation of a straight line. If x is 0, y is 0. If x is 1, y is minus 1. 0, 0, 1, minus 1. This is a straight line which cuts across like that. Okay, y equals x is the 45-degree line. This is like the 135-degree line. Now, what about the graph of this function here? With a square root, the best thing to do is to square both sides to get a feeling for what we're talking about. And when we do that, we recognize an old friend. Here we have a circle, okay, centered at the origin, radius 3. However, because it was the positive square root, it's the top half only of that circle. So a circle centered at the origin, radius 3, but only the top half of that function. We don't have the bottom half because it's only the positive square root. When you see the square root, it implies the positive square root. And finally, over here, we have another straight line. If x is 0, 2 points determine a straight line. So if x is 0, y is minus 3. If y is 0, x is 3. So we have it goes through 0, minus 3, and 3, 0. And it looks like that. Now, let's see what we're going to do. According to the function here, we're supposed to take the line y equals minus x if x is less than 0. Okay, so I'm going to take I'm taking my scissors and I'm going to cut right over here. I'm going to take this portion, okay? I'm going to take the line up to, not including the origin, because it says if x is less than 0. So I'm taking the line y equals minus x when x is less than 0 to the left of 0. Now, between 0 and 3, we're supposed to be on that circle. Well, actually, the top half of that circle. If x is 0, y is 3. And if x is 3, y is 0. So we're going to take the portion of the circle from 0, 3 to 3, 0, including the endpoints. This portion we're going to cut from here, from 0 to 3. Then, when x is greater than 3, we're supposed to go on to the third function, which is a straight line. Now, it said when it's greater than 3, at 3, y would be 0, but we don't include that point. And we just take from the right here. Okay, so let's put these three pieces together and get the graph of the original function, f of x. See what we have. We're supposed to take y equals minus x up to, but not including the origin. And then from 0, 3 to 3, 0 here, we're taking this portion of the circle. And then finally, we picked up this other line here. Now look, this was a filled-in point at 3, 0. This was an open circle here at 3, 0. But when we cut and paste and put them together, this open hole is going to fill right over that point. So the end result is that it's going to be connected here. And the picture will look like that. Okay, so here we have the graph of y equals f of x. We took the line y equals minus x if x was less than 0. Between 0 and 3, we took this portion of the circle, including the endpoints. And then finally, we took the line y equals x minus 3. Okay, so we've put this together. We have sketched a graph of the function. Okay, now we've sketched the graph of the function. Now we're going to answer the two questions. What is the limit of f of x as x approaches 0? And what is the limit of f of x as x approaches 3? Now, when you're dealing with split functions here, you have to be careful in evaluating these limits. We could answer the questions about limits from the picture. You should be able to do it from the sketch, but you should also be able to do it just strictly from the definition of the function. Okay, looking over here, as x approaches 0, the limit as you approach 0 from the left is not equal to the limit as you approach 0 from the right of this function. As you approach 0 from the left, the function values are getting closer and closer to 0. As you approach 0 from the right side, the function values are getting closer and closer to 3. Okay? Since the limit as you approach 0 from the left does not equal the limit as you approach 0 from the right, this limit will not exist. Now we have the graph of the function. We can do it this way. But let's say you didn't have the graph of the function. How could you evaluate this limit just strictly from the definition of the function? We would know that the only way we could investigate the limit as x approaches 0 of f of x is to look at the limit as you approach 0 from the left and the limit as you approach 0 from the right of this function. Now, the whole trick in a split function is simply what to substitute for f of x. Okay? There are three choices here for f of x, depending on where you are. Now, as you approach 0 from the left, you are to the left of 0. You are less than 0. Well, if you're less than 0, then the function is supposed to be minus x. And that's what we do. We're over here. We're going to say the limit as x approaches 0 from the left. In this case, the function is minus x. Okay, let's say we didn't even have the picture. We want the limit of f of x as x approaches 0 from the left. Okay, think of the number line. We have, here is 0, here is 3. As you approach 0 from the left side, this is the region where you're less than 0. This region is between 0 and 3. This is greater than 3. As you approach 0 from the left side, you are less than 0. So you take the part of the function that's less than 0, which is minus x. You substitute that for minus x, and now you evaluate your limit as always. What's the limit of minus x as x approaches 0? You let x be 0, minus 0, or 0. Now, the limit of f of x as x approaches 0 from the right. As x approaches 0 from the right side, well, both of these portions are on the right, but immediately to the right is the region between 0 and 3. As you approach 0 from the right, you're between 0 and 3, you're supposed to replace f of x by the square root of 9 minus x squared. As you approach 0 from the right, you are greater than 0. You're between 0 and 3. Replace f of x by the square root of 9 minus x squared. And evaluate this limit by substitution. The square root of 9 minus 0 squared, the square root of 9, which is plus 3. Since the limit as you approach 0 from the left does not equal the limit as you approach 0 from the right, the two-sided limit, the limit of f of x as x approaches 0, does not exist. Geometrically, what we're saying is that as you approach 0 from the left, the road that you're taking ends at a point whose y value would be 0. As you approach 0 from the right, the road that you would be taking ends at a point whose y value is 3. It's only when these roads come together that the limit will exist. Since the left-sided limit was 0 and the right-sided limit was 3, the two-sided limit does not exist. Now let's do the same thing, but this time we're evaluating the limit of f of x as x approaches 3. we're going to have to look at the limit of f of x as x approaches 3 from the left, and the limit of f of x as x approaches 3 from the right. And once again, the key is going to be which portion of the function should be substituted for f of x. Now, as you approach 3 from the left, let's go back over here. As you approach 3 from the left, you're between 0 and 3, the function should be the square root of 9 minus x squared. However, as you approach 3 from the right side, when you are greater than 3, for that we'll substitute x minus 3 for f of x. So as you approach 3 from the left, these are both on the left, but this is immediately on the left. The 0 to 3 section, the function is the square root of 9 minus x squared. As you approach 3 from the right, you are greater than 3, we're going to use x minus 3. So let's put these values in here. As you approach 3 from the left, you are between 0 and 3. We're going to take the square root of 9 minus x squared. As you approach 3 from the right, you are greater than 3. We're going to use x minus 3. These limits can now be evaluated by substitution. The square root of 9 minus 3 squared, the square root of 9 minus 9, the square root of 0, or 0. Here, as x approaches 3, 3 minus 3 is also 0. Since the left-handed limit is 0 and the right-handed limit is 0, since they are the same value, you write down their common value for the two-sided limit. So the limit of f of x as x approaches 3 is 0. But the limit of f of x as x approaches 0 did not exist. Once again, geometrically, at 0, the road from the left and the road from the right did not come together. At 3, however, the road from the left and the road from the right did come together. By the way, if this had been an open circle, that would not have affected the value of the limit. It's what's happening as you get close to 3. So if this had been, open, it still would have had the same limit. The road from the left and the road from the right have to come together at a point, even if that point is not part of the actual graph of the function. But here, the road from the left ended at a point whose y value was 0. The road from the right ended at a point whose y value was 3. That limit at 0 does not exist. At 3, the road from the left ended at a point whose y value was 0. The road from the right ended at a point whose y value is 0. And the limit as you approach 3 is considered to be 0. And that brings us to the end of this tape.